Guys, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this particular discussion, I'm going to look at the concept of matrix multiplication, and this is going to be creating a very important aspect for us in trying to evaluate other aspects of matrices like determinants, cofactors, and of course the inverses, which we are going to be particularly meeting in our subsequent video. Now, in this case, I'm going to consider finding the product of matrices which are going to be either an n by 1 or 1 by n, which is going to be either a single column or row kind of matrices. And this is going to be, of course, entailing the concept of a dot multiplication of matrices. And in my subsequent statements, I'm going to be performing some of the symbol evaluations, and we're going to come up with particular, of course, rules which are going to be assisting us in trying to evaluate the different sets of matrix multiplication. And I'm going to look at this one by considering two specific matrices, which are going to be represented by A and B given as such. So let A and B be matrices of order which we can give in terms of n by 1 and 1 by n. So this we said going to be forming a single, of course, what we refer to as columns and rows respectively. And these are going to assist us in trying to evaluate the various aspects of matrix multiplication. So this, they can be represented using this specific, of course, notation, whereby we're going to have the matrix of A being represented by elements of A1, A2, A3, and these are going to go on to a value of AN. And we can represent the matrix of B as well using the elements of B1, B2, B3, to a value of Bn given as such. So for us to evaluate such a kind of a matrix, we are going to perform what we call a dot product of this matrix of A and B. And this is going to be denoted using this specific, of course, representation of A dot B given as such. And of course, the summation of this one is the product of this one can be given as a summation of multiplication of the respective elements, which are going to be element of A1 and B1. And of course, it's going to be forming a sum of these specific elements going in this particular order to a value of n given as such. So basically, we can represent this dot product of a matrix of A and B for this specific form given using this particular order, whereby we're going to see that this basically is going to be giving us a summation of the elements from I is equals 1 to, of course, the point of n, which we have given for the last element of the specific matrices of A and B of AI, BI given as such. So this is going to be forming a representation for a formula for the representation of a dot product of two matrices given for A and B of such a nature, which we have given on the upper right side of upper, of course, a section of the board as shown as such. So we can take a specific example for us to do an evaluation and see how this one is going to work out for such a kind of a matrix, which we have just done a general case for A and B. So let these specific matrices of A and B be represented for, let A be given in terms of the elements of 1, 2, and 3, and B be given using these specific elements of 2, 0, and 1. So we're going to do an evaluation by considering this specific aspect of the elements of 1, of course, which is going to be forming A and B. So we are going to take this particular, of course, relationship which we developed from our subsequent statements, which is going to be A1, A2, B2, plus this range of values for elements of A and B, the sum of the product of A and B to n value. And this is going to be given in terms of 1 times 2, the sum of that one, plus 2 times 0, the sum of that one, plus 3 times 1 given as such. And this is going to be giving us the value of course, 5. So this is going to be 2 plus 0 plus 3, which is going to be giving us 5. And this is going to be forming the product of this specific element. So in our subsequent discussion for the general case, whereby we give a a sum of AB, which was given in terms of I plus 1 to a value of n ai bi, we're going to see that this is going to be forming what we refer to as a scalar quantity, and therefore we're going to see that one being the same implication for the value of 5. And this we're going to be performing particularly the range of values for the dot product of such a kind of matrices. So we shall look at the second case whereby we are going to be performing operation of multiplication for matrices of the form of m times n, which particularly notes the 1 by n or n by 1 such a type of matrices, such as the one that we have just done for the of course previous example. So we shall have this one given in terms of a matrix of A being represented by various elements which are going to be consisting of ith rows and kth columns. And we're also going to look at a matrix of B being represented by these specific elements of B. Of course, we're going to have this one k and j columns given as such. So if you have such a kind of a matrix, we're going to see that these basically are going to be matrices of the form which we can have for A given in terms of m times n. And these are going to be matrix of the form m times s given as such. So this is going to be m times s given as such. So if we consider their respective, of course, elements in terms of rows and columns, we're going to see that A basically given as this specific combination. Of course, we're just going to give it as that. I'm going to elaborate on the various columns and elements as a product. So we're going to have A given in terms of AK and B given in terms of kj given as such. So as we can see, these are going to be forming the first rows are going to be, of course, of different kinds for I and k. But as we are going to see, we are going to have a k and k. So this is going to be the k for the column of A and the k for the elements of the rows of B. And therefore, the combination of the two are going to be giving us a product which is going to be given in terms of AB, which is going to be an M by S a kind of a matrix. So we're going to see that the elements which are going to be having that specific connection are going to be, of course, negated and giving us a product of this specific case. So we're going to have a general way of representing such a kind of matrices, whereby the matrix of A and B is going to be giving us a product of a C. So therefore, we'll just have this one given in terms of this one, a product of a C, which is going to be an M by S kind of a matrix. So therefore, we are going to consider this specific element. If we consider this one to be particularly given in terms of ik, and then we have this one given in terms of a kj. So we're going to have the product of elements consisting of I and S, which is going to be I and of course M and S, which is of course going to be I and J. And therefore, these are going to be the product of this specific element, which we expect them to be the elements of the columns and rows of this specific product. So therefore, we are going to obtain this specific by having the general representation of A, B given in terms of A, I, K into B, Kj given as our product. And this is going to be representing our C, which is going to be, of course, what I've just basically mentioned on the upper section of the board. So we can give a general representation of this specific product of Cij, given in terms of the product of Ai and Bj, which are going to be giving us the sum of elements from k is equivalent to 1 to a particular value of n over Aik and Bkj given as such. So this is going to be forming a specific representation for various range of values for such a kind of matrix, which are going to be an m by n or an n by s given as such. And they're going to be forming a general case for representing the subsequent types of matrices for such a kind of examples. So let's have a general case and try to see how we can represent that one. Or just a specific case which is going to be assisting us to represent the same. So suppose we have a matrix which is given in terms of A, which consists of elements of 6, 4, and 3. And then we're going to have -2, 3, and -1. And then we're going to have 1, -1, and 2. And B consisting of elements which can be given in terms of 2, 1, 1, and then we're going to have 2, 5, 7, and then 3, 1, 1. So we're going to perform a range of course, multiplications which are going to be giving us values of this specific kind. So if we are requested to find the product of particularly the square of a and a, b, and b, a, we can perform a range of operations by having this one, the square of this one, given in terms of a is equivalent to 6, 4, 3, negative 2, 3, negative 1, 1, negative 1, 2, 6, 4, 3, negative 2, 3, negative 1. This is going to be 1, negative 1, 2. So we have come across the various ways in which we are going to perform an operation for various sets of matrices. And this basically is going to be a multiplication of the various rows and columns for the first, of course, row and the first column, which basically means that we're going to perform an operation which entail so I'm going to do the first example on how we can find the product. So we're going to have this specific element of A11. So which implies that in this case, if we're going to have the product of the two, we're going to take the multiplication of the first row with the first column for the subsequent, of course, or the kind of a product. So we're going to take the first row of this one and the first column of that one and find the product of the first element of the product, which is going to be 6 times 6 for the first row given as such. 6 times 6 plus, so the sum of that one, 4 times negative 2, which is going to be 4 times negative 2, plus 3 times, so this was positive 1 given as such, which is going to be particularly this specific value. So we're going to have 3 times 1, which is going to be basically giving us 36 minus 8 plus 3. So this is going to be giving us a value of 31, which is, of course, 28 plus 3. So this is going to be giving us a value of 31. So basically, we're going to perform those specific operations using the various range of ith row and the jth column of the individual elements. So in this case, if we had this 3, 2, 2, we are going to take the second row and the second column and try to find those specific products. So the product of the square of A is going to be giving me these specific values of 31, 33, and the last one is going to be 20 for the first row, and then I'll have negative 19, 2, and then negative 11, and then I will have 10, negative 1, and 8 for that specific product. So kindly confirm from your end whether we are going to find this specific element for the product of the square of the two, of course, a set of matrices for A. And of course, I'm going to find this specific product for AB, giving me the range of values 29, 29, and then I'm going to have 37. And of course, I'm going to have negative 1, 12, 18, 6, negative 2, and negative 4. And for mine, my side, of course, I'm going to find the product of BA equivalent to this range of numbers 11, 9, 17. And I'm going to have 10, 16, and of course 14, 7, 15, and then 10 given as such. So in this case, this is going to be the product for my side of this specific evaluation for the product of A and B given as such, and B and A is going to be given as such. So if I try to look at a specific characteristic for the second option for B, we're going to see that basically if I interchange the position of these specific matrices for A and B for B and A, I'm going to find a different product. So this gives us an idea that basically if we have a matrix which is going to be given as a product of A and B, so this is not equivalent to B and A. Therefore, a multiplication of matrices is not going to be giving us what we refer to as a commutative property. And this, among others, are going to be assisting us try to pinpoint some of the characteristics of our matrix multiplication, which are going to be widely applicable in our subsequent discussion on the concept of a classical adjoint, the inverse, and determinants of various other sets of matrices. So kindly check our description boxes for various links of other videos. Engage us in the comment section, subscribe, and also ring that notification bell for other updates on different uploads in math and sciences. So that is it for now, guys. By God bless you. Catch us in our next video.